Hello and welcome back. Today we have 652 Find Duplicate Subtrees. It says given the root of a binary tree, return all duplicate subtrees. For each kind of duplicate subtree, we only return the root node of any one of the duplicates. So only one of the duplicates will return. Two trees are duplicate if they have the same structure with the same node values. So 2 and 4 and 2 and 4, these are both the same structures and the same values. Whereas if there was another 4 down on this side, this would not be the same because the structure is not the same. So the way we can actually do this is by taking into account for the path. Each of these paths will be unique. Each node will have a path of its own. Well, not unique, but each node will have a path of its own. Then we can keep track of how many times we encountered that path. And if we encountered it never before, we can add it to our map of counts, which we'll initialize. If we encountered it once and only exactly once before, then we can add it to our result. Let me try, you know what? Let me try results. Results, we'll say result is going to be initialized to some value. Okay, and then we're going to have some mapping of counts. Where the key will be the path and the value will be the numeric count, the count. Okay, so maybe this is easier. Okay, so and given that we are trying to get the path of each node, we do need to process all the children beforehand. So essentially, if we're starting from the root node, we're starting from the We're starting from the root node. We cannot fully process this path before we process everyone else. So let's go left to the end. We're here finally. This is the leaf node. There's nothing to the left. Okay. So this path we can represent as 4 and some string to represent empties. We can do like a hash, for instance, and that's to represent this node. Okay, and this we haven't yet encountered, so let's add that here. So for hash hash is a path that we have not yet encountered, so let's add 1. Okay, now we got this guy. How do we process this guy? Can we process this guy? We can, because we have the left, we have the right. Right is null, so right is essentially just the hash. Then we start on the current node, which is 2. We take the entirety of the left, which is 4, hash hash, and then the entirety of the right, which is a hash. Okay, so again, that's 2, 4, hash hash, hash, 3 hashes. Now this also we have not yet encountered, so we can add it to our counts map with a value of 1. Now we want to process this guy, but can we? We cannot, because we need all the children before we can do this. So let's jump to the right, or this child, missing child, and then we always go left, right. So let's jump to the left, We're finally at a place where it has no children of its own. This one, take the self, and then the left, which is empty, so that's a hash. A right, which is empty, so that's a hash. Now this, have we seen this before? We have, it's right here. And in exactly 1 count, which means though it is a duplicate, indeed, we have not previously added to our result. So let's do that. Result is now going to be, I wonder if it'll let me edit. Ah, yes, okay. The result will now have 4. Okay, we just added the 4, and don't forget, we also need to increment this to 2. Now this is 2. We have 2 instances of this path. Okay, Now 2 over here, also, we start from ourselves. I'm at 2. Its left is a 4 hash hash. Got it, 4 hash hash. And then its right is empty, so that's another hash. And 2, 4 hash hash hash, we have it here. And this also, it is a duplicate because it's already in our map, but it was not previously added to our results. So let's add it to our results. We'll add the root, which will essentially have the pointers to all its children, so it'll be represented like so. And then make sure to increment this to 2. Okay, so 3 will be this plus whatever this is. Oh, we cannot process the 3 yet. We haven't yet processed this guy first. Okay, let's process the children first. 4, again, it's 4 hash hash. All right. And this is also here. However, now this is a 2. 2, meaning it is a duplicate. It is in the map. However, it's greater than 1, so we previously already added to our results. And because we are only returning only one of the duplicates, we can continue without re-adding this. So now we have both children, and 3 becomes 3. The entirety of this one, which is 2, 4, hash, 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 ooh, hash, hash, hash. Okay, the entirety of this guy and the entirety of this guy, which is a 4 hash and a hash. And this does not exist in the map, so let's add it with a count of 1. Okay, so we have this, this guy is right here. And this, now we can process, this is the addition of this. So it's the addition of itself, 1 plus this guy, plus this guy, which is this guy. So let me type it out. So it's the self plus 2, 4 hash hash hash, 2, 4 hash hash hash, and the right, which is all of this, which is 3, 2, 4 hash 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 4 hash 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 hash. Okay, so this one, this entire thing is the path, and then obviously this doesn't exist in our map. So let's add that. And by this point, we're done processing, and we have our results. Okay, so let's translate this to code. We have a DFS function that takes in some node. We're gonna do stuff to it, but first let's initialize our count default tick to int, so that if the key doesn't exist, it will default it to 0. Okay, we have the counts, and then we're going to make sure to not forget to call it using our root, starting on our root, and then we also need results, where we'll store our duplicate, or nodes of the duplicates, and we'll return the results. Okay. So in our DFS function, the standard base case is if not node, we can return some character. Let's say it's a hash, and then remember we do need both subtrees, all of our children, to construct the full path. We cannot construct the path of this guy before we have it for this guy, which itself needs this guy. This guy needs both guys, which includes this guy. Okay. So left is going to be DFS of node.left. Right is going to be DFS of node.right. And then only we can construct our path, which begins with us, node.val. And then it's whatever left is and whatever right is. Then we do want to add or increment this path because we encountered it. We need to keep track of it. And ultimately, we do want to return this path. So let's make sure to do that because that's what will be returned in our left and right. But also, now this is the key, also, if before we increment it by 1, if counts of path is currently exactly 1, then it means, yes, it is a duplicate. It does exist in our mapping. However, it was not previously added to our result. So we can go ahead and add it to our result. So let's do that. Let's dot append. And we are returning the root. So let's return our current node. Okay. I think that's it. Let's see. Let's try. Okay, let's submit. Oh no, hold on. Where did I go wrong? So if I don't have a node and return the hash, I'm preprocessing the node on left, preprocessing the node on right. My path is whatever the current value is and whatever is the outcome of the left and the right. If the counts of path is exactly 1, then I want to add this node. And whatever it is, I want to increment it by 1 and return path. Counts rows. What's wrong? Let's see. Let's plug this in. Okay. Let's plug it. That looks like that. And so there are no duplicates. This one has no duplicates. But what do I return? 11, 1. Why do I return 11, 1? If not node, return 0. Node dot val. Do I need commas, perhaps? That might be it. Okay. So the reason being, I thought it might be worthwhile going over the one that error and why we need delimiters. Okay, so in the previous, before adding commas, I was returning 11.1. However, we were expecting empty because there are no duplicate subtrees with the same values and the same paths. However, note that this is 1, this is 1, 1. So let's just take it slow. Let's run through this. Okay, so let's run through this. So we start at the 2. We want to process 2, but we need its children first. So we go here. We need, for this, we need here. So we're here. This one, it does call the left and the right, and those both will return hash. And those are the base calls, okay? So now we can construct the path for this, which is you take the self and the hash and the hash, okay? And see how we're already running into trouble. 11 could be 11, or it could be 1, 1. Let's continue. So, and then if we come to 1, and we can add that here, 11 hash hash, and we'll correct this. Right? Okay, so 11 hash hash, we have a count of 1. Now once we get here, this one calls the left is fulfilled, the right will ultimately return a hash. Then we'll construct this using a 1, and then the entirety of the left, which is 1, 1, hash hash, 1, 1, hash hash, and whatever is on the right, which is a hash. Okay. So this guy might be easier. Let's see if I can do this. 1, 1, 1, hash, hash, hash. So this one is also 1. Okay? So now we want to do this guy, but we can't until we have all the children in order to construct a full path. So we try to process this guy, but this guy can't be completed until it processes its children. So let's start on the left. The left, this one essentially becomes itself 1, and it's left, which is empty, it's right, which is empty. Okay, and we can add that here as well. We can add a 1 hash hash along with a count of 1. Okay, and then once we have processed this guy, we can finally process this one, which is going to be the left. No, it's the self first, then the left, then the left, which is that hash hash, and then the right, which is empty. Here we have the problem. Okay, the problem is we don't have any commas or any delimiters. This is from one single node. So this one is the value from the current node. This one's the value from its left, or part of the value from the left. Whereas this guy, although as a string with no delimiters, it's the same. It represents different things. Where here, this one single digit represents the child value versus here where 2 digits represents the child value. And these 2 digits, hold on. These two, it's swapped. These 2 represent the current value, and this single 1 is part of the child value. So they're swapped. However, because there's no delimiters, this, essentially what would be this, is being conflated with what's essentially this. So hence the commas. Okay, so here, instead of adding it straight like 111 hash hash hash, we can return 1 comma 11 hash hash hash, which is 1. And here, then, it's not this, it's actually 1 comma 1. Let's maybe be consistent, so it'll be something like that, and that's 1. Okay, so this will also be 1. Let's just fulfill it. 1 comma 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 comma. Okay, and this will be 2. 1 comma comma. This will be as well. I think you get the idea. But yeah, that was the main point. The delimiters are required because otherwise we can't differentiate when there are more than 1 digits. And to finish out, once we add the delimiters, and it can be any delimiter that does not duplicate this at least, then we are successful and decently efficient. Once again, this was 652 Find Duplicate Subtrees, a medium problem today. And yeah, there you go. Happy coding. See you next time.